Hello, welcome to our 14C lecture on gas laws. Today is actually going to be on the ideal gas law, so we're stepping it up a notch. First of all, though, I'm going to let you grab a piece of paper to take notes since these are not in your notes packet, so I will give you a second to do that. You can just insert the Jeopardy theme song here. Just kidding, you can pause it. So, we shall move on. An ideal gas is a gas whose particles take up no space, have no intermolecular attractive forces, and do not condense into a liquid at low temperatures. So we ask ourselves this question: are all gases ideal? The answer is no. None of them are ideal. They all have volume in their gas particles. That's pretty much the definition of matter. And they're all subject to intermolecular interactions. The greatest deviation from ideal gas nature happens at extremely high pressures and low temperatures. What happens when you get to high pressure and low temperatures is that at high pressure, you're forcing the gas molecules closer together, which makes it easier for those intermolecular interactions to happen, and they actually can be strong enough to make the gas turn into a liquid. And that is very far from ideal. At low temperatures, you're slowing down the molecules so much so that they can actually have their intermolecular interactions happen, and then they also, under that condition, will form into a liquid. So here we have our ideal gas law. It's PV equals nRT, with P being pressure, V is our volume, N is our moles, R is the universal gas constant, so we'll talk about that in a sec, and T is our temperature in Kelvin. Always, always, always in Kelvin. By now we're pretty familiar with our combined gas law, which is P1V1 over T1 equals our P2V2 over T2. And this one was great for looking at what would happen to the gas when we change one of the variables. So if we decrease the volume, what would happen to the pressure and temperature? If we increase the temperature, what happens to the volume or the pressure? Well, now we're just going to look at what happens, not when something is changed necessarily, but what are the conditions for a gas at specified pressure, volume, temperature, or amount. So that's what we're going to look at here. Now, back to our lovely new R constant. This is called the universal gas constant. It is different, it varies with the pressure units. So here we see one value for R, which is 0.0821 liters times ATM over moles times Kelvin. So this is what we would put in for R if we had ATM as our pressure unit over here. Now, if we had kilopascals, we would use 8.31 as our R value. If we had joules, we'd use 8.314. And if we had torr, we could use 62.36. So you have to be very, very careful about which R value you use. You do need to memorize this R value and this R value. So the one for ATM and for kilopascals. Now, once you figure out what units and you have the right R, we are good to go. So let's take a look at a problem. So at 215 kilopascals of pressure and a temperature of 318 Kelvin, 2.35 moles of a gas have what volume? So since we have pressure, volume, and temperature, and we're not going from one set of temperature, pressure, volume, numbers to another, we know we're going to need to use our ideal gas law. So we're going to write that out. PV equals nRT. Now, let's just plug in our numbers. So we have 215 kPa and a volume is what we're looking for. That's going to equal 2.35 moles times our R constant. Now, which constant are we going to use? So we're in kPa. So if we look back at the chart on the previous page, we find kPa right here, and we're going to use 8.31. So we'll go back, put in 8.31, and that's going to be liters times kPa over our moles per Kelvin. And lastly is our temperature, which we have at 318. Alright, so now if we take a look at our R constant, it actually functions to help us cancel out units. So here we can cancel out Kelvin, we can cancel out moles, and our kPa values, when we divide, are going to cancel out as well, leaving us with liters. So once we do the math on this, so you're going to multiply 2.35 times 8.31 times 318 and divide it all by 215, we are going to get 28.8, yes, that's an 8 liters. So that is our final answer. So let's take a look at another one. Here we have 23.5 grams of a carbon dioxide gas at room temperature of 45 degrees Celsius, and at a temperature of 45 degrees Celsius and a pressure of 125 kPa. What is the volume of the container? So first thing we are going to do is actually switch our 45 degrees Celsius, because we can't do anything in Celsius, to Kelvin. So we're going to add 273, and that's going to give us 318 Kelvin. Alright, so now we got that. We're going to use our PV equals nRT. And now we're going to plug in our values. So we have pressure of 125 kPa. We're looking for the volume. Now, moles. We're given grams. What can we do to get to moles? We are actually going to divide by the molar mass, because that will give us moles. So, molar mass of carbon dioxide is 44 grams, and that's going to give us 0.534 moles. So now we can plug in our 0.534 moles times our gas constant. We're going to use our 8.31 kPa times liters over moles times Kelvin. And lastly, our temperature. Once again, we just crank this through our calculators. 0.534 times 8.31 times 318, all divided by our 125. And that's going to give us 11.3 liters. See? Easy peasy. Now it's time to get a little more exciting. So, this question asks, what is the molar mass of a pure gas? So, if we have PV equals nRT, do we agree that N equals moles, which equal mass divided by the molecular mass, or the molecular weight? So we can actually substitute this in and get PV equals mass times RT over the molecular mass, or the molar mass, or the molecular weight, however you want to say it. So this is actually equivalent to our N. So since we made that substitution, we can actually solve now for the molar mass. So we have M equals MRT over PV. But wait, if we have mass over volume, what does that equal? And look at our equation, it's asking for density. Conveniently, these equal density. So we can rewrite our equation one more time. 2B, molar mass equals density times R times T all over P. And now this is the equation we're going to actually use. So we have 1.40 grams per liter times STP. I am going to use ATM for my R value, so it's going to be 0.0821. And then since it's at STP, that's standard temperature and pressure, I'm going to use 273 Kelvin. And it's all going to be over 1 ATM. See why I chose ATM? Makes the math real nice. So 1.4 times 0.0821 times 273 is going to give us a molar mass of 31.4 grams. Lots we can do with this equation. Let's check out another problem. So, this question asks, what is the density of a gas at STP that has a molar mass of 44 grams? So this time, we were given molar mass. So we can actually rearrange our equation to solve for density this time. So when we rearrange this equation to solve for density, we get density equals molar mass times pressure over RT. Now, all these variations are great equations to write down. That way you don't have to figure them out every time. So my molar mass was given as 44.0 grams per mole. And at STP, I'm going to use 1 ATM again because it just gives friendly numbers, all over standard temperature of 273 Kelvin. And because I chose ATM here, I'm going to use 0.0821 ATM times liter over my moles times Kelvin. There we go. So we just do 44 times 1 divided by, and make sure you double parentheses or bracket the bottom so that you get the right number. So 44 divided by 273 times 0.0821. And that is going to give you 1.96 grams per liter. And that is our density for this gas. Pretty easy. Just lots of variations on the same equation. Thanks for joining me, and make sure you take your quiz for 14C after seeing this. Have a great day.